Hi everyone, welcome to tutorial 79 of our introductory Python for image processing tutorial series. In this tutorial, let's implement the plan that we have discussed in the last video, which is read an image and corresponding mask or a labeled image and train a machine learning model. Let's try both random forest and SVM, support vector machines, and create a model that we can use to segment future images that look very similar to the images that we have used for training, of course. So I'm dividing this into three parts. In the part one, this video, let's just use a single image and a single mask, and let's understand the basics. And in the next video, which I hope will be a very short video, let's take a trained model and then segment a whole bunch of images that are in a folder. And then in the third video, let's do something very similar to this video, except instead of using one image as a mask, let's use a folder full of images as training images and training masks. Okay, so that's the plan. So let's jump in. Just to quickly remind you, what we are trying to do here is take an image and corresponding labeled image. And in the last video, I showed you how to create one of these. Please go to www.appear.com, APEER.com, sign up, upload your images, go ahead and paint the pixels, and save your labels. So once you have this, we are going to extract features and capture all the extracted features into a data frame, a pandas data frame, and train a machine learning algorithm. So that's the plan for today. Okay, so now let's jump into our Python Spider IDE. Again, please do not look at all of this code. Let's actually go through this a few lines at a time so it makes sense for you. Okay, so first of all, let's import our standard libraries. I always import NumPy, OpenCV, and pandas because I seem to be using that in pretty much every piece of code. And I have my train images sandstone. So let's go ahead and let me open the images so you can see exactly what we are talking about. So I have a folder called train images right there. And I have the images that I'm planning on using for training. And I have the corresponding train mask appear. And again, for those of you who did not watch my last tutorial, this is how a mask looks like. So for example, this is the mask for an image that is the first one right here. So if I open this, you can see. So this is my original image and this is the mask. And the bright regions are corresponding to some of the labels that I hand painted within these bright regions, and other regions correspond to these other regions here. Okay, so that is the plan. So first let's go ahead and use only single image in this video. Okay, so I'm going to use OpenCV to read this image. So when I do that, I should see, if I go to Variable Explorer, my image is 1024 by 996. That's a relatively large image and 3 channels. I'm reading it as color. I could directly read it as gray by putting as gray or just doing that. But since I haven't done that, let's go ahead and add another step called color, convert my BGR image to gray. Okay, you can do this in single line if you want, like I said. So now if you look back up here, my image is now a grayscale image. Again, we have done this numerous times in our previous videos, so let's not spend too much time here. Now, one thing I should mention is if you're actually reading a multi-channel image, for example, if you're reading CZI or multi-channel TIFF like OME TIFF images, obviously instead of converting them to gray, just extract the relevant channels. For example, if you have a DAPI channel represented in channel number 3, then just extract that for your nuclear segmentation. Okay, so once you have that, now my image is 1024 by 996. Let's reshape it into one single column because now we have to create, our goal is to create a data frame where each column represents a different feature. Our actual pixel value of original image is a great feature. Yeah, in fact, histogram segmentation, that's exactly what we do. Use the pixel values to segment the image. So let's go ahead and reshape it. When I do -1, it means just go ahead and do it into single column. So as you can see, we have 1024 multiplied by 996, that many. If I open this, you should see that I have a whole bunch of zeros. And then if I keep going down, you should hopefully see other values show up. A lot of my image seems to be filled with black pixels, but if I keep going down, you should see some real values right there. Okay, so this is my image, I called it image2, but let's actually capture these values into a pandas data frame. Again, I assume you have watched my videos and you're trained on pandas. So let's create an empty data frame and then add a column to that empty data frame called original image and add the pixel values, which is image2 right there. So if I open my data frame, you should see that now I have index and then original image, and this is all the pixel values that are coming from this specific image, from our training image here. Okay, I hope so far so good. Now we defined that Gabor would be a great way to generate features. So I have written, again, this is exactly the same code that we have generated as part of our Gabor tutorial. So here you can change many parameters, but as you can see in the Gabor kernel, it's a function of kernel size, sigma, theta, lambda, gamma, and one other parameter right here, which I coded as 0. And then, so now we can generate as many Gabor filters as we want just by changing these values. So in this example, I'm changing theta 2 times, and I'm changing sigma 2 times, 1 and 3, and I'm changing lambda 4 times here, range of wavelengths, and then gamma is 0.05 and 0.5. You can add more. Again, it takes more time for training. And not every Gabor is useful, but we don't know which one is going to be useful. We'll find that out at the end of this tutorial, which Gabors worked, which did not. So we don't waste all the time, and we can just use those ones that actually work. Okay, so this piece of code, all it's doing is going through these for loops where we change theta, sigma, lambda, and gamma. And for each of those values, it's going to generate a Gabor kernel and append it. And then it's going to apply that onto our original image, which is our image2 right there. In fact, I could have changed this to original image, which is img, which is a 2. Let's actually do that. I don't know why I did image2. So, okay. Because this is a 2-dimensional, this can be applied. The way we designed this is a 2-dimensional kernel. Okay, so we are going to apply that onto our image right there, okay, which is 1024 by 996, okay? And the filtered image is also going to be a 2-dimensional image. So let's go ahead and reshape it into a single column and add that to our data frame, okay? This filtered image values. And the data frame column name, I'm calling it Gabor label, which I'm changing it each time the Gabor changes. So it would be Gabor 1, Gabor 2, Gabor 3, and so on. So that's all this is doing. So let's go ahead and run this piece of the code. And at the end of it, we should see about 30, I believe, if my math is right, 30 to 32. Yeah, about 32 of these Gabors. And if I open this, let's continue anyway. That's tremendous amount of data. It's warning us there's a lot of data. As you can see, the first column was original image, where the pixel value is 0. I'm not surprised that Gabors are also giving a 0, but let's not worry about the values. Let's just go and see. We have 32 Gabors right there. Okay, so after 32 Gabors, and by the way, we are going to drop pixel value 0. If you remember, pixel value 0 means these are all unlabeled pixels. So there's no point. In fact, we should not be training it on that. Okay, so we'll get there in a second. But in addition to Gabor, I'm adding a few others so you know how to do it. Okay, so I'm applying canny edge, I'm applying Roberts. Again, I made individual videos on each of this topic. So hopefully you watched them and now you know what we are talking about. And I also created Gaussian filtered images where sigma equals to 3 and sigma equals to 7, because we don't know which one works the best. And median image with sigma equals to 3. So let's go ahead and also add these columns. So let's run these lines of code. And now if I open it, again, it should warn me that there's lots of data. And if I open this and slide it all the way to the right-hand side, you should see after Gabor 32, we have columns for canny edge, Roberts, Sobel, Scharr, Pruitt, and Gaussian sigma 3, Gaussian sigma 7, and median sigma 3. So these are all added to my data frame, the pandas data frame. So at this point, we have the X values, which is the features. We are training the features, and then we have to tell it to model the ground truth, which is our labels. So let's read the label file. So in this case, we are reading the label file, and let's go ahead and read it. And what did we call this? Labeled image. I just want to make sure it does make sense. Yeah, labeled image is 1024 by 996 by 3. And we are converting that to gray again, or you can read it as gray to begin with. And now we are reshaping it exactly what we have done before into a single column. And now I'm adding another column to the data frame called labels. And here again, let's open our data frame, which we call df. Sorry, right there. And we should see that the last column is called label, and most of it will be labels 0 because we have a lot of unlabeled pixels over there. So if I slide it, you'll probably see one somewhere, but it's going to take a lot of time. But let's not worry about that yet. We'll get there in a second. So now let's go ahead and there is a reason why I'm saving this. Because once I train this model, I want to apply it to this entire image, including the pixels where we haven't labeled anything, and then segment that image to make sure that everything is working fine. To do that, before I drop any of the labels, or any of the data, I want to capture that, okay? This entire thing that we have into a new data frame called original image data. So if you look up here, I have original image data, which is basically a copy of my original data frame, except for the column labels. Okay. And why did I do this? Again, I want to use this as my test image after I did my training. Okay. We'll get to this in a second. Now I'm ready to drop all the pixels with a value equals to 0. The way I'm doing this is my new data frame, which I call df, is nothing but my old data frame, which is df, where the data frame labels are not equals to 0. So let's go ahead and run this line. And now our df should have much fewer data points, only 74,000, because all the zeros are gone. So it's not 1 million anymore or 10 million anymore. So if I open this and look at labels, now you see all the real values showing up because we dropped all the pixels with a value of 0, which are unlabeled. So my label 1, again, label 1 in our image. Do I still have this open? Yeah. Label 1 in our image is all these purple regions that represent pores. Label 2 is, I believe, these green regions, which is what we define next. Label 3 is quartz and label 4 is pyrite. I think one of these regions, we have very few of them, but let's see, label 1, 2, 3, 4. Okay, so this step, we make sure all the values with 0 are dropped. And again, this is unique to this process where you're labeling images in Appear. If you label them somewhere else and where you have labels at every pixel, you don't need this line, okay? So again, I'm just showing you with this data set, these are the steps. Okay, so now let's separate this data frame into X and Y. Y is the value that we are trying to predict, which means our labels. So my Y is basically an array that says 1, 2, 3 or so, okay? So 1 is all the, let's go down. You see we have 1, 2, 3, and again, this is at every pixel. What is the label? And our one thing I added here is a label encoder. This is an optional step. Right now, you see the Y values are going from 1, 2, 3, 4. Now, normally, if you would like to use some of the standard built-in metrics evaluators, like in scikit-learn, for example, is it in scikit-learn and also in other modules, there is something called ROC AUC. Again, that's beyond the discussion of this video. I'll get to that in one of the future videos. But a lot of these built-in libraries, they assume that the classes are 0, 1, 2, 3. Or if your labels have a value of, I don't know, 200, 30, 42, or if your labels, instead of having values 1, 2, 3, 4, if they're actually text, like background, and clay, quartz, how do you use them in your training? So this is a great way. If you do use label encoder, it actually encodes every label into a value of 0, 1, 2, 3, 4. This may sound a bit counterintuitive, but again, hopefully read up on this topic. This can be very useful for you. So when I do that and open my Y again, instead of 1, 2, 3, 4, now I have 0, 1, 2, 3. Like I said, this is an optional step. If you think this is confusing you for now, you can skip this part. Okay, but this step is almost a necessity. If your input data, for example, is not image data, but it's coming from some other data source where the labels are, is this malignant or benign? Okay, so you cannot just model the text malignant and benign. You have to convert that into 1 and 0. Okay, so 0 and 1 classes. So that's a quick example I can think of. Okay, so that's we just encoded our values. Now that's our y. Y is ready. These are the values we're trying to predict or trying to model to. And x is basically all the features. So in our data frame, every column is important except for the column labeled labels, because this is our y. Okay, so let's go ahead and drop that. And our x is basically everything but labels. So far our x is, I believe, yeah. So let's go ahead and open so you can see what x is. So x is basically original image pixel value, Gabor 1, Gabor 2, Gabor 3, 4, 5, and so on. It appears right away that Gabor 1 and 2 are probably not that useful. I don't see any numbers. I only see 0. So not much signal is going through, but maybe some areas you're getting some signal. It's tough to predict anything just by looking at this data. Okay, so that's your x. Like any other machine learning, we are going to split this into training and testing so you can do some validation. Again, we have done this quite a few times in the last few videos. So we are using scikit-learn's train test split to split it into 80% training size and 20% testing size. That's what this represents. Okay, so now we have everything ready, and doing actual machine learning is very simple. All you got to do is, okay, what machine learning model do you want, or classifier do you want? In this case, from scikit-learn.ensemble, let's pick random forest classifier. Make sure you pick the random forest classifier and not regressor. As the name suggests, random forest regressor predicts a continuous value, and classifier is just a classifier. It's classifying into one of the many bins. Okay, so I'm training a model using this random forest, and number of estimators, let's just put 10 trees, or let's actually do 20 trees for now. And random state, let's just keep it to 42, and let's run these lines. And now let's fit it to our X train and Y train. This should be very fast, even though we have a lot of data. This should be relatively quick. You see, a few seconds there. So now I have a model ready to be used. Now let's go ahead and predict this. But before predicting, one advantage of random forest is that it tells us which features actually worked well and which features did not work well. So let's go ahead and print out a feature importance. Again, I may have covered this in my random forest tutorial, but the feature list, if you just look at feature importances and then just get once a model is trained, you can just do model.feature importances and it reports the feature list. So just read these couple of lines of code and look at the printout here now. So let's move this a bit and then look at that Gabor 1 and 2, just like we predicted, its contribution towards this model is practically 0. So most of these are not useful. So why waste our computing power to train? I mean, in this case, I am not, I'm using pretty much everything to train. But in future, if you want to deploy a model, you may as well ignore all of that and only look at the top 10 or so that actually work. So it looks like Gaussian with a sigma value of 3 is giving us 18% of contribution, and then 15% is median. And then the original pixel values also mean something Gaussian. Gabors seem to contribute a bit over there. So that's what feature importance actually mean. Okay, so while we're there, let's go ahead and train a support vector machines. Again, support vector machines, just like in the previous tutorial where we looked at it, I'm using linear SVC with a maximum iterations of 100. Let's go ahead and train it. Why am I doing this? So we can compare random forest and support vector. And you'll see that support vector machines is a tad bit slow compared to random forest, but is it worth the time? I'm also including the code for logistic regression if you want to compare it. So I'll share the code on GitHub like usual. And the link is in the description down below. And let's go ahead and predict using both random forest and support vector machines. Okay, now let's go ahead and look at the metrics. And the metrics is basically we are comparing the prediction versus the actual. actual label. That's pretty much it. So let's go ahead and print these values. And you see random forest, I got 96% accuracy, and with support vector machines, I got 87% accuracy. I see that for most of these type of problems, random forest does a much better job than support vector machines. So there you go. And I am also including a piece of code that reports something called ROC AUC. Okay, and what that does is it actually prints these plots, and this plot is for random forest and this one is for support vector machines. And if this is a great classifier, then the model would look like a line going up here and then a line going up here. And random forest is almost a perfect model. It's doing great. And AUC is area underneath the curve, and area underneath the curve, if it is 1, that means it's 100% accurate in a way. And if I go down to support vector machines, you see how these are going down. And by the way, this line right here represents a random pick, meaning if I randomly pick one pixel and assign to one of the 4 classes, there is 25% chance that I get it right, basically. So this is the random line. This is basically a chance line right there. And the closer these curves get to this chance line, the worse the model is performing. So visually, you can see that random forest is doing much better than support vector machines, although support vector machines is not that bad. So I'm going to include that part of code for you. Now let's go ahead and make a prediction. First thing first, let's save this model. And I'm going to save it using pickle library. And it's called, I'm giving a name called sandstone_model. So let's go ahead and save it so I can use it later on. And once I save it, to load this model, again, I'm going to do pickle.load. In this case, we don't have to do that, but just so you know, we are saving and then we are loading it. And once you load the model, I give it a different name, loaded_model. I could have just done model.predict, okay? Because we are still in this code. Okay, so let's go ahead and we already dumped it. Let's predict it onto our, by the way, original image data. Remember, we took an extra step up here to save our original image data right here, where we dropped all the labels. Normally, you can just use X, but in this case, it will give you an error if you do X, because the X is basically after dropping the values of 0. So it's not your image shape anymore. That's why I saved it before dropping the values of 0. I hope that makes sense. So if you look at original image data, where is my original image data? We should have our, how many, 10 million? Yeah, so our 10 million pixels right there, 1024 times 994 or something, okay? So when we reshape it to original shape, it should look like an actual image. Okay, let's come back. So let's predict it onto our original image. So that's what we are trying to do. And by the way, the original image data is not just the image pixels. It's after all the filters. Whatever you're predicting, it has to go through these filters. And then you apply the model onto that data frame. So now that we have it, I'm reshaping it. Okay. And let's go ahead and show it on the screen. So, oops, sorry, let's do that. And when I open the plots, and here is the result. So we are predicting or segmenting this image, and that output doesn't look that bad actually. You see all these regions and then the outer regions in blue, and these clay regions, you see those textured regions right there in cyan over there, and everything else in yellow. I think that's a great segmentation, even though we haven't labeled a lot of pixels. And typically, this is why I prefer random forest over deep learning if I don't have a lot of training data. Okay, so I hope you found this tutorial to be useful. In the next tutorial, let's take this trained model and apply it to a whole bunch of images in a folder so we can save them as segmented images. By the way, in this case, we are reading these individual files. Now, if you read a TIFF stack, please read them accordingly, and then we'll cover that in a couple of tutorials from now. But until then, please go ahead and subscribe to this channel, and let's meet again in the next tutorial.